Welcome to our lectures on the DC microgrid and the control. Today we are going to discuss a very important topic, that is the stability analysis of the DC microgrid. So, in the recent years, in order to we have discussed in detail the necessity of the DC microgrid, and for this reason control of the DC microgrid is the ultimate necessary, and the stability problem of it, how we will solve, we will going to analyze by this lectures. So, in the recent year, in order to solve the energy storage, the microgrid has gained more and more attention and applications, because we have seen the disadvantages of the conventional grid, and now with the high penetration of the renewable energies, we are gradually moving towards the microgrid. Compared to the AC microgrid, the DC microgrid has several advantages. DC microgrid has the advantage of simple control, because it has only it does not have a different entities like voltage and the frequency like real power, imaginary power. So, you require only to control the voltage, and thus control is simple, and it is highly efficient because absence of the reactive component of the power, KVA rating of the coil is same as a resistive rating, and for this reason it is highly efficient. And also when it is transmit the high frequency power at the 50 hertz, and it is feeding adjustable loads and all those entities, then this supply may have the 5th, 7, 11, 13 and other harmonic, and due to the skin effect, effective cross sectional area get reduced, and ultimately you will have a higher resistive losses. And since absence of the frequency makes this system frequency higher, highly reliable, we ensure the reliability mostly by bipolar connections, and since there are no power quality issues, so there is no problem of the power quality in DC microgrid. You do not have a problem of the THD, you do not have a problem of the power factors, these are missing. So, and for this it is good power quality and it is highly reliable. However, DC microgrid contains a large number of load converters. So, different load require a different level of power supply, and thus we can plan accordingly, but we are living in an age of the transitions, since most of the systems are AC. For this reason DC load are not been properly standardized, that is one of the greatest challenge. If you have standardized also the DC load, then this issue can be negated at a large extent, but from the today's perspective we will have a large number of the load converter. One may take 5, for example, laptop chargers takes 18 volt, your mobile chargers takes 5 volt. So, why can't we have a only single kind of entity where laptop charger rather than mobile charger can be used? And thus what happened, which are the characterized by the constant power load, that is one of the features of the modern devices. These are mostly the constant power load, that is called CPLD in abbreviation. And since if the voltage, one of the major problem is having a CPLD in the system, that if voltage drop, then it will track more amount of current and it will take the system towards the instability. And thus what happened, the cause of what happened with the large number of constant power load caused the instability of the DC bus of the microgrid. So, let us take a typical microgrid which has been shown in this figure. A typical DC microgrid structures is shown in the figure 1, which contains large number of power electronics converter. You have a grid for, you have a active rectifier, mostly this is at the higher voltage side. You have a bidirectional DC to DC converter. It depends, battery mostly is around 48 volt, and your bus voltage may be close to that or little different, or maybe some other voltage. You have a very first charging and discharging ultra capacitor or the super capacitor, and there might be a load can be directly connected to the DC bus voltage 48 volt, and there might be a DC to DC converter, that because this supply, this bus voltage and this load require a different kind of supply. This is a wind. Again we have a rectifier followed by a boost topology DC to DC converter that will fit, and since it is boosting for the MPPT, so then you require to have another DC to DC converter to balance the voltage level of the DC bus. Same way for the solar, you got a solar DC to DC converter, ultimately you will track the maximum power point. Please understand that maximum power point tracking is challenging. Many of you have studied the maximum power theorem in your early days of your BTech. So, when source impedance equal to the load impedance, then only you will be able to transmit the maximum power. So, that is the criteria. For this reason, you require to manage the impedance, so that the source impedance equal to this site's impedance, and thus maximum power will be transmitted from this PV cells or the wind to the bus voltages. So, when the load point converter works in a constant voltage mode and the control performance is good, the load point converter and the load is relative to the DC microgrid, referred as a constant power load, or in abbreviation we sometimes say CPL, and if it is device then it is CPLD, constant power load device. Under normal weather condition, when solar is healthy and you have a plenty of wind, maybe the distributed power such as the photovoltaic and the wind power is generally works at the point of maximum power point. So, it has to track the maximum power. So, it can harvest the maximum power from these sources. At this time, load converter can be seen as a constant power load. That is something also we require to understand. So, since it is transfer, impedance matching and all those things, so that can be seen as a constant power source. Now, let us have a system model, and we may have a boost topology in case of the mostly tracking solar MPPT, and in this case where it is replaced by your E, it can be the solar panel. And thus what happened in the following this situation, in which boost converter maintains the DC bus voltage of the microgrid, we require to analyze it, and we have a constant power load. Let us see. So, what happened, we know that actually it has a two states, when switch is closed and when switch is open, and this topology a simplified DC microgrid is shown in the figure 2, which distributed power source is connected to the DC bus voltage by the boost converter, and the circuit equation is shown in the figure 3, and this is the equivalent circuit model of the DC microgrid when switch is off. That means this switch is off, and it does not, when this voltage and this voltage are same, generally this switch is off and you will transmit the power, since the losses across the inductance is 0. And thus if you say that when switch is off, duration is d, when you have substituted, that value will be 1 minus d. For this reason, when switch is off, this equation is written. So, L di dt equal to E minus 1 minus d into UC. UC where is a voltage across this capacitor. Similarly, this will be C dV dt or C duc dt equal to 1 minus d into IL minus U c by R plus, since this point voltage is U c as has been mentioned here. So, the current drawing by this constant power load will be power of this CPL by the voltage of U c. So, ultimately the current drawn entity will be totally depending on this voltage of this boost rectifier. And please understand that there is a challenge, and please refer back this characteristics equation 1, that is this is linearized in the equilibrium point of the system, and the condition of the system can be obtained, that the load, that is constant power load, should be more than U square by R. See that what is R? So, this is your R. So, this is the power dissipation across this resistor, normal resistor. So, what happened? Power of so the power of the constant power load is stable system, but must be less than that of the resistive load, then only it will work fine. However, in a typical DC microgrid contains about, this is one of the challenge, that 80 to 85% of the constant power load, you have a huge constant power load, ultimately all your SMPS in your laptops, desktop are constant power load, and only 20% to 15%, that is the heating load, are resistive. So, that it will face a lot of challenge in the stability. So, for this reason we require to take some measures to ensure the stability of the microgrid. The interaction of the electrical systems around the DC bus cause the instability in the DC bus, that is also one of the observed phenomena. So, electrical subsystems, its impedance matching, how it will work, this also forms a localization problem, and the phenomena of instability is considered then as the consequence of the connection of the constant power load in a DC bus. When there is an element present which regulates the power consumption of the load, for example, your inverter, your converter, battery, etc., it is possible to assume to have these loads, that is aforementioned load, having a constant power load behavior. So, they also behave like a constant power load, and for this reason in a microgrid CPLD constitute around 80% of the loading. So, what happened? Then when you connect a CPL or D, the device connected to the DC bus, then we require to understand that the control of the load, when the control of the load will then set the load to compensate the disturbance of the bus. When there is a voltage drop, since CPLD takes a constant amount of power, then it will track more amount of the current from the system, and thus it will pull down the voltage level further. So, that is one of the greatest challenge in the CPLD. On the other hand, when you have Worthman and Road and you got a little bit of, or you got a more DC bus voltage, and you want by loading to bring down the voltage level, since it is a CPLD, your voltage level is high, current will be drawn less, and thus it will further push up the voltage. So, in the language we can write like this: the load does not take into the account of the electrical state of the network, including the DC bus. It is seen by the DC bus as a constant power consuming element as shown in the figure. So, it is just P by V. So, P is constant. So, this is the electrical system containing nonlinear load, and the output of the source converter is represented by the voltage source E here, please refer back the figure. This output of the source converter is considered as a voltage source, it is E, which interface with the filter circuit. Mostly you may have a high frequency ripples because of the switching, and you got to eliminate those ripples, consisting of the equivalent series resistors and the inductor and the capacitor with the nonlinear load. A nonlinear load is presented by the current source and having a characteristics P by V, where V denotes the voltage drop over the capacitor. So, this is the voltage across the capacitor, and the current absorbed by this constant power load on the DC bus can be modeled as shown in equation 3, that is P by V, where for a given given operating point V 0 I 0, the output of the voltage and the current are kept constant. The introduction of the constant power load in the networks implies the appearance of the nonlinearity of this PV tie. So, it is not V square R kind of load, it is P by V kind of load. If voltage increases, current will decrease, if voltage decreases, current will increase. And thus, this is the characteristics of, and it will be a rectangular hyperbola, and this is the operating point, that is the I 0 is the maximum current and the V 0 will be the optimal current, optimal voltage, and you supposed to operate here. If you go here, you will have a, that is a problem here also, because you have a more voltage, less current, and here if you go, you have a less voltage, more current, and operating here it will be detrimental, because you are not operating rather this point, you rather shifting to this point, and it will cause huge amount of instability. The rate of change of the current can be obtained by the linear approximations of this equation 3. Please go back to this equation, and a small area around the operating point, let us say this neighborhood, and here you are supposed to operate the CPLD well. The linear equivalent of this resistance of the CPLD given operating point of this equation 4. So, just you have this curve and thus you get a derivative of it. Once you derivative with respect to V, you get P V square, and you can replace this thing V square by R, and thus you get P by R CPL, where R CPL is it may be observed from the equation 4 that R CPL depend on the actual voltage and current. So, it will be a changing depending on the voltage and current, since this is your curve. So, this point you have a different tangent and this is different tangent, and essentially this gives you di dV characteristics. This curve represents the current versus voltage for CPL and can be approximated by the straight line and tangent to the power curve at the operating point, and the equations can be given as it can be represent that the constant power load resistance CPL equal 2 I 0 minus 1 by R CPL, that is 2 PV P by V 0 minus P by V square into V. This will be the overall expression of the resistance. Since this power is constant, ultimately this resistance definitely depends on the output voltage of this DC bus voltage. And now, let us come to this operating point issues, that is the operating point of the CPL has a behavior similar to that of the negative resistance in parallel with the constant current, and that has been shown here. So, electrical behavior of the CPL amount operating around an operation point or the operating point is depicted in the figure 6. This is E, you have a filters, and ultimately it is the to balance out the instantaneous power balance, you have a capacitor, not only filtering, because sometime if load may take little bit of more power or less power. So, that something transient has to be fed to this capacitor. So, you can model this as 2 p by V plus this resistance, and thus this circuit diagram of this figure 6, which is we have shown in the figure 6, can be represented as dV dt equal to minus 1 by C R CPL V plus 1 by C V and di dt equal to minus 1 by L S minus R by L S. So, the linearizing the Jacobian, we can rewrite this equation in a state space form, and ultimately V I and I I will be have this resistance which we have mentioned here, and capacitor by inductor and RL. And let us form the polygonal one, and you have a study over your eigenvalues, and thus you have this eigenvalues. So, from this characteristic polynomial we can deduce the relationship in a next equation 10, which states the criteria of the eigenvalues of the system for the negative real part. So, thus from this condition we can get, this is essentially nothing but your maximum power transfer theorem you get by this calculation. So, RCPL equal to minus R, and this one is should be less than minus L by RC. And thus what we can say here, the first inequality holds because the negative sign of the of this, because you know that it is a negative resistance region. So, it is RCPL, and usually equivalent series resistance R is very small when comparing to the absolute values, and while the second will not always be respected, since increasing the load power causes the increase in the current, which has a consequence over increasing the value of this RCL. Thus, by replacing this RCPL by inequality relations, which we have shown in the equation number 11 is obtained, and which gives you the local condition for the stability. And thus what happened, that P should be minimum of RC by L V square by R. This should be the power. And it is quite important thing, though it is very simple. The relation P is less than V square by R is less restrictive than the relationship, that is you got it in case of the maximum power transfer theorem. Please remember that is your power should be less than your V square by 4R, and which ensures the existence of an operating point of the system, while the relation 11 gives the stability conditions of the operating point. This is the stability condition of the operating point. So, you have to operate within this region. So, while going through this analysis, what we can say that this equations 11 is quite important and it required to be satisfied while you are designing the CPLDs. Now, as we can see that the dynamic condition of the CPLD in the microgrid. So, it can be seen that in equation 10, this is your equation 10, this is a constant you have put, that is RCPL should be less than minus R and RCPL should be less than L by RC. So, these are the two constraints you have to put it into this condition for deriving stability. So, it is seen from the equation 10 that the relationship between the stability of the system and the so sizing and the sizing of the filters, the RLC and also the source voltage of the converter and the power consumed by the local load can be expressed. So, what load this CPLD will deliver, ultimately all have a say on it, and to transfer this maximum power you want, definitely you want to be systems to be stable as well as your efficiency should be high. So, all those parameter has to be designed properly, and all this parameter has a huge say, and thus it has been seen that the capacity of the inverter, generally this inverter comes into the picture from the active rectifier. If you are taking power from the grid or you are sending back to the power to the grid, then it is in an inverter mode, increases the system and becomes more stable, and vice versa for the inductance of the filter. You can make it also converter for DC to DC conversion. It applied both for the AC microgrid. So, what happened? It can be seen that this is the criteria where maximum power required to be transferred and stability, because this is the criteria of maximum power transfer. And so, please see these two equation and compare and see that it is there already, and thus we can conclude that while the limitation puts by this equation, while this eigenvalue has been real negative. So, all those put into the consideration, we can design a proper value of the systems, and in that way you can calculate the proper parameter, and with high CPLD in the DC microgrid, we should be able to control and appropriately work as per the requirement in case of the transient as well as the stability as a large. So, this is something quite important aspect for a little deviation from the normal weight because of the less resistive load. If you have a resistive load, it is itself has you have a leeway, because if voltage decreases, then you will consume less amount of power though, but current also get reduced. Ultimately, you can overcome this problem easily. And on the other hand, once your voltage is more, then you are going to increase your current, and thus you are going to consume more amount of power. You would like to bring down this mismatch. But here with the CPLD is Watson, and for this reason the stability study is quite important, and we require to map that properly. Thank you for your attention. We shall carry out our discussion on the stability of the microgrid in our next class.